This is the new course description. We'll be having, starting this week, we'll be having 3 lectures per week, Thursday, Friday, and Saturday. The lectures will all begin at 8:30 p.m. Eastern Standard Time. For now, we'll be having 1 office hours per week on Sundays, but the day and the number of office hours may change. We haven't decided on the time of the office hours, but we will announce it at the lecture this week. The first lecture will be Thursday, June 17th at 8:30 p.m. Eastern Standard Time. And throughout the 15 weeks, we'll be covering most of the highest yield MCAT content, okay? So this is the GroupMe link. Learning objectives for today are enthalpy, entropy, and internal energy, Gibbs free energy and spontaneity, how work and heat are involved, and changes in temperature and state. First, we want to cover what are thermodynamics. Thermodynamics refers to the changes in energy and state of a reaction. The main application of thermodynamics in biology and chemistry is to track and predict changes of reactions in molecules. One of the most important topics and one of the most important quantities in the universe is entropy. It is essentially a measure of the randomness of a system or of the universe. The entropy of the universe can never decrease. There can never be a chemical reaction that will decrease the entropy of the universe as a whole. However, there can be chemical reactions that decrease entropy of a small system in the universe as long as the surroundings of the system increase entropy at least as much as the system decreases. And if you see this equation at the bottom, the entropy of the universe equals the entropy of the system plus surroundings. So I'm going to draw this picture. So if there's this big circle, and this big circle is the universe, it's everything that exists. The system is the small square inside the universe that we are observing. The surroundings is all of this shaded region outside of the system, but inside the universe that we're not observing, right? So as mentioned, the entropy of the universe as a whole of this circle cannot decrease, but it can decrease for this small square in the middle. If the entropy of this small square decreases, it would, unless otherwise changed, would decrease the entropy of the whole circle as a whole. In order to combat that, we have to increase the entropy of this shaded region outside of the square by at least an equal amount in order to counteract that and make sure the entropy of the universe doesn't decrease, right? However, the opposite is not always necessarily true. If you increase the entropy of this small square, you don't necessarily have to decrease the entropy of this outside shaded region by an equal amount in order to balance it, because it is okay for the entropy of the universe to actually increase, right? What entropy means is, and what going from low entropy to higher entropy means, is going from an ordered state to a more disordered state. And a disordered state or a random state is the preferred state for most molecules and the universe as a whole, as we understand it. So there are many ways to change the entropy of a molecule or system. The main way is through state changes. A gas will always have more entropy than a liquid, which will always have more entropy than a solid. As you can see in these state diagrams, which I'm sure you've seen many times before, gases are free to move around. And because of that, each gas molecule, each circle, has many different positions or locations it could be in at the same time. And that gives more potential for randomness because there's many more different random positions that it could be in. A liquid is more packed together than a gas. Because of this, there's many less potential locations and states and positions it could be in, and that decreases entropy of a liquid as compared to a gas. A solid is very rigid to the point where the molecules can't even move. They can only vibrate or rotate. Because of this, the entropy of a solid is very, very low because there are very, very few potential positions and locations each molecule can occupy. Another common way to change entropy is through temperature. If you increase the temperature of a molecule, you increase its entropy. This is because increasing temperature increases kinetic energy. If you see these gas molecules, they have these arrows which indicate that they're moving and bouncing around. If you increase the temperature and heat these molecules up, they'll actually move much faster through space, right? When they move faster, that increases their kinetic energy. And entropy has a unit of joules per Kelvin. Kinetic energy represents the joules, right? As you increase kinetic energy, you increase the joules of the entropy related to the entropy. You also increase the Kelvin, which is the temperature, but by a much lower amount than the joules, right? An unproportional amount. So by increasing the joules and increasing the numerator of this unit, you increase entropy as a whole, and that's how you can think of it. Or you can think of it as speeding up the molecules will allow them to be in more possible positions at any given time, or take more potential states at the same time. If we're talking about a chemical reaction, delta S, which is change in entropy, usually has units of joules per Kelvin mole, right? Because most reactions are on a per molar basis. Enthalpy is another very important quantity in the universe, and it's a measure of the total heat content of a system. Enthalpy is a derivative of internal energy, which is the measure of heat energy. The formula is enthalpy equals internal energy plus PV, which is pressure times volume, right? Internal energy is what we think of when we think of heat or like fire or anything like that, right? Since enthalpy comes from internal energy, which is a form of energy, conservation of energy also applies to H. Energy cannot be created or destroyed, so the total enthalpy of the universe never changes. It always remains constant, unlike entropy, which can increase or stay the same. However, enthalpy of a system, the little tiny square in the big circle, does change. And when it does, the enthalpy of the surroundings, the shaded region outside the square, changes by an equal amount, an equal but opposite amount, right? And this is to maintain that, that conservation of energy. If it didn't change by an equal but opposite amount, you would either create or destroy energy, which is not allowed. Enthalpy is commonly used to measure the favorability of a reaction in terms of heat. For example, if a reaction has a delta H that is negative, that means the reaction releases heat to the surroundings, which is favorable. If the delta H of a reaction is positive, it absorbs heat from the surroundings, which is not favorable. These are called exothermic and endothermic respectively. If it releases heat, it's exothermic, and you can think of it as exo is outside, so releasing heat to the outside is exothermic. Endo means inside, so absorbing heat into inside yourself means endothermic. The unit for enthalpy is joules. As mentioned, it's similar to energy, and it is a form of energy, so it's joules, just like energy. And delta H, just like with entropy, is joules per mole in a chemical reaction, because chemical reactions typically have a per molar basis. Delta H of formation is an easy way to find the delta H of any reaction if you're given the delta H of formation of the reactants, which is this delta and this small subscript F. So as you can see, each of these chemicals in this reaction have a delta H value, heat of formation, right? And if you notice, it's kilojoules per mole. So something like, for example, water, which is negative 241.8 gaseous water, and there's 2 moles in this reaction, so you would take this and you would multiply it by 2 when you were putting it in the equation. The delta H of the whole reaction, which is Rxn, is equal to the sum of the delta H of formation of all of the products subtracted by the delta H of formation, the sum of the delta H of formation of all of the reactants, right? And we'll cover that in this question. Okay, I'm gonna end the poll in about a minute or two, so get your answers in if you haven't already. By the way, if you guys are using calculators, I would recommend against it. For now, maybe it's fine, but I would recommend against it in the future because on the MCAT, you're gonna not have calculators. So you should be able to do something like this, like on pen and paper, if you have it, right? Okay, so I'm gonna end the poll. Okay, so most popular choice was choice C with choice A and D following. The correct answer is actually choice E. Oh, well, I said choice A was actually choice E, right? So choice E was actually the correct answer. And the reason is, like, and Opal mentioned this in the chat, you can't actually eliminate any answers unless you do the math. Like, if you were to look at the math, you like just off your head, you'd probably be able to eliminate choices A and B because they're too big. But other than that, not really. And sometimes you want to just do the math anyway. So the way you'd set it up, like I mentioned, you'd sum the delta H formation of the products and then subtract the delta H formation of the reactants. So you have something, let's say, so CO2 is, so the delta H formation of CO2 is negative 393 plus negative 241. Multiply that by 2 because there's 2. So because there's 2 waters, right? 2 moles, and this is per mole. So you'd multiply by 2. And then you take all of this, you subtract CH4, which is negative 75, plus O3, 143. Right? And you'd be able to do, so this is about negative 500. Total, that's about negative 893 about. So again, with the MCAT, you can do approximately. And plus, so negative, so this would total to be 75 minus about 75, and you'd get something close to this. You'd get negative 900 something, which is close to E. And I know I didn't list E as an option. I mentioned that you should, if you were to choose choice E, you would choose choice A instead. Yeah, so somebody asked in what instance are coefficients not taken? Yes, in determining order of reactions, coefficients are disregarded. When you're determining order of reaction or rate of reaction, that's a different topic. For this topic, you have to take it into account, especially because they give you on a per molar basis, whereas there's 2 moles of water here.
Mark, you have CO. Are we using CO or we're using CO2?
We're using, so be careful with this because they'll give you a lot of lists. Always use like CO2, like always use like this. Always use like the ones they give you. Sorry, yeah. Okay, does that make sense? Okay, cool. Next, we want to look at Gibbs free energy. So how do we determine if a reaction is overall favorable or not favorable, right? We know if it's favorable through entropy, and we know if it's favorable through enthalpy, right? But how do we know if a reaction, like for example, this reaction is overall favorable, right? Well, we use the quantity of delta G to determine that Gibbs free energy. Delta G is a measurement of a reaction to determine if the reaction is favorable overall, taking into account all factors, right? And if it is favorable overall through delta G, it will occur spontaneously. meaning that it will occur without any outside interference, right? So it'll naturally happen, the reaction. Whereas if it's non-spontaneous or not favorable, it will never happen naturally. You would have to either have some, it would require some kind of interference. So from an outside source, some other outside source would have to give up its energy or push energy into it in order for the reaction to occur. Okay, so like I mentioned, some reactions have a positive delta S, which is favorable, but a positive delta H, which is not favorable, right? So it's hard to tell, what is the reaction as a whole, favorable or not favorable, right? Well, you would use delta G in order to really see if it's favorable or not favorable as a whole. So the formula for delta G is delta G equals delta H minus T delta S, right? And we know what delta H and delta S are, and T is temperature in Kelvin. That's important note. Most of the time, especially in thermodynamics, temperature is always in Kelvin, not Celsius, and definitely not Fahrenheit, right? If delta G is negative, the reaction is exergonic and favorable. If delta H is positive, the reaction is endergonic, unfavorable. This follows the same rules as delta H, but different rules from delta S, right? If it's negative, it's favorable. If it's positive, it's unfavorable, just like with delta H. But whereas delta S is the opposite. Positive is good, negative is bad. And the naming is very similar, exothermic or endothermic. It's exergonic, endergonic. Looking at this simple math, if delta H is negative or favorable, and delta H is positive and favorable, they'll both be favorable, and delta G will always be negative, right? No matter if you have a negative value here, minus, and this is a positive value, so negative value minus a positive value, it's always going to be negative, and it's always going to be favorable. If delta H is positive, which is not favorable, and delta S is negative, which is also unfavorable, so you would have a positive value minus a negative value, which signs would cancel out, and it's positive value plus positive value. Delta G would always be positive. There's no other way around it, which is unfavorable. The problem comes when, say, delta H is negative and delta S is negative as well. They're both favorable. What happens then? Well, at higher temperatures, delta S is more important or wins, while at low temperature, delta H is more important or wins when determining favorability, right? So you can see that mathematically. If delta H is a negative value, which is favorable, and delta S is a negative value, which is unfavorable, if the temperature is small, if it's a low temperature, this whole side, so let me annotate this. This whole thing will be small, right? Because the temperature is small. So multiplying a number by a small number makes the whole thing small. And in that case, delta H would be, it would have a negative value minus a negative value, signs cancel out. So it's a negative value plus a positive value, right? And if the negative value is bigger, then the overall would still be negative. If, however, you increase the temperature, temperature is very high, delta S wins because this value is big. If you have a small negative value plus a big positive value, the result's a positive value, which is unfavorable, just like the delta S. That may be a little bit confusing. Do you guys have any questions or anything about it so far?
What was the first scenario without the temperatures? You described the scenario without the high temperature and low. You told us the positive when delta H and delta T, when delta H is positive, delta S is negative, then we get unfavorable positive. So what was the scenario without the temperature? What was, without high, what was that?
I can explain it this way. If the reaction is favorable, both in terms of delta H and delta S, the delta G will be favorable. If the delta H and the delta S are both unfavorable, delta G will be unfavorable, regardless of temperature, right? It doesn't matter what temperature. If both are favorable or both are unfavorable, the result matches with the favorability.
What were the signs when you said when they're both favorable? So they're both favorable when delta H is negative and delta S is positive, right?
So in the chat, Janelle put the Gibbs energy chart. So if you click on that image and download it, you'll be able to see
Thank you.
the exact chart, right? Yeah, I would agree that like these, yeah, this chart is very, very helpful.
Thanks, Janelle.
Okay. Anybody else have any questions? I think somebody else maybe had a question. If not, move on. Actually, okay. So we have a quick question coming up. So if you have a question, please feel free to ask. If we can, yeah, we can repost the chat here. I'll start the poll and then I'll repost the chart. Okay. Okay. Poll is up. Okay. Okay. So the most popular answers were B and C. The correct answer is actually A, not B or C. So if we want to look at this, if we want to look at the question, so we know that it has a negative enthalpy. Enthalpy I mentioned is H, so it has a negative delta H and a negative entropy, which is negative delta S. We know that a negative delta H is favorable because I mentioned negative delta H is favorable and positive is unfavorable. Whereas with entropy, it's the opposite. A positive delta S is unfavorable, whereas a positive delta S is favorable while a negative delta S is unfavorable, right? If one is favorable and the other is unfavorable, in terms of delta G, we wouldn't be able to determine it without knowing the temperature as well, right? So with that, we can eliminate endergonic and exergonic all at the same time, right? Because delta G could be positive or it could be negative depending on the temperature. However, we do know the delta H, so we can definitely know whether it's exo or endothermic. I mentioned that negative delta H is favorable, which means it's releasing heat to the environment, which is exothermic. If it was a positive delta H instead, then it would be endothermic, right? And that's why this is the correct answer. Does that make sense? Gonics relate to delta G, positive or negative delta G, whereas thermic relates to positive or negative delta H, right? They're different.
We only use the gonics when we're talking about the temperatures, or?
We only use the gonics when we're talking about delta G. So gonic relates to delta G. Thermic relates to delta H. We don't know what it says which the following terms necessarily describes the reaction, which are we certain about? Because the delta G can be positive or negative, we don't know if we can't say for certain it's exergonic or endergonic. We can't say for certain if it's endothermic or exothermic because they told us what the sign of enthalpy is, right? Does that make sense?
That makes sense. Thank you.
So if the question stem doesn't mention delta G, yeah, so if it doesn't mention delta G, sometimes you can, but usually no, because if you know what the enthalpy is and the entropy is, sometimes you can figure out what the delta G is. So you know that delta G equals delta H minus T delta S, right? That's the equation. If they're both, so if enthalpy is negative, yes, if both of them were favorable, it would be exergonic, right? Exactly. If both enthalpy and entropy are favorable or both are unfavorable, we know if it's exergonic or endergonic. Whereas if they conflict, one is favorable, one is unfavorable, unless we know the temperature that we're looking at, we can't know if it's endergonic or exergonic. But yes, you're right in the chat. If both are favorable, then it's exergonic. So if both delta H is negative and delta S is positive, right? And is everybody clear, like the favorability between enthalpy and entropy? Is that something people are still confused about? Like when delta H is favorable, when is delta S favorable? Okay, so no, if anybody is, please put in the chat or speak up, because that's like the key to all of this. If you don't know those, you can't really move on. Okay, I'm gonna clear all drawings and move on if nobody has any other questions. Yeah, the chart should help. Okay. Next, we're gonna move to delta G and K equilibrium constant. This is a very small, short thing, but something I feel I should mention. So there is a relationship between delta G standard. So with standard means with this little degree sign here, and KQ. And this is very important, and I'll get more to it later. Before I move on, I want to make sure in the chat, both exergonic, both H and S unfavorable, endergonic, negative H and negative delta S exothermic, positive H. So yeah, in the chat, what Shrika posted, the first two are definitely right. The second two it's true, but exothermic and endothermic only relate to delta H, right? So yes, that's right. But the first two, so in point A, yeah, in terms of the question we got, yeah. But the first two are also exogonic and exothermic, endergonic and endothermic as well, right? But yes, you're right. In terms of the question we got, yes. Okay. So that's good. And if you have a question, please refer to her, because that's right. Okay, so moving on. So as I mentioned, delta G standard, which I'll cover the difference between delta G standard and delta G in a little bit, but delta G standard and KQ. So the formula is this: delta G standard equals negative RT ln K, and this is KEQ, but we just call it K, at equilibrium. And this is important, it's at equilibrium, right? And R is the gas constant, which you guys probably have heard before. Same one as in PV equals nRT. This is the same R as in this equation. It's 8.314 joules per mole per Kelvin. On the exam, always, like whenever you have R, remember R is in joules. So if you have a delta G, a delta H, anything in kilojoules, you have to convert kilojoules to joules, or joules to kilojoules, either way, it doesn't matter. But notice that R is always in joules. So if the delta G is in kilojoules, make sure to convert. There's also, so this is really like just a formula you have to memorize. I'm not going to go into depth really on and yes, so what John put in the chat was right. But yeah, this is an equation you just really have to memorize and just kind of like work with it when you have these values given. I don't really want to go too far in depth with what it actually like means and how it's derived and all of that, because that's, first it involves, I think, some calculus to derive the equation, and it's not necessary. There's also this formula, delta G standard equals negative RT ln Q. What Q is Q is K when it's not at equilibrium. So K is an equilibrium constant. It's always at equilibrium, right? If you have a K, that means the reaction is at equilibrium. Q you use when the reaction is not at equilibrium, but it means essentially the same thing as K in that sense, right? But it could be delta G standard equals negative RT ln K or Q, depending on whether or not it's at equilibrium. Okay. Does this make sense? And I'll try and explain more at the end, especially with what delta G standard is, okay? But any questions so far? Okay. So we have another using that formula. So we have another quick question. So I'm going to post this. Okay, so you guys can vote. This uses that equation I just posted, so please have at it. So this question is possible without a calculator because they don't ask you to solve it. They ask you to leave it in terms of E. Without a calculator, it wouldn't be possible if they asked you to solve fully, but if they ask you to leave it in terms of E like this, it is possible without a calculator. You don't need a calculator for this. It involves a little bit of simple math, but other than that, it's not as complicated as you may think. Okay, I'm gonna close the poll. So most people picked, so we had a pretty big spread, but most people picked B, which is actually not the right answer. The correct answer is D, and I can tell that you guys had trouble with this, and I'll go over it. So we know that the equation is delta G equals RT ln K. So first step is to identify what they're actually asking for, right? So they asked, what is the ratio of ADP to ATP equilibrium, right? So that is actually exactly equivalent to K. So what they're essentially asking for is what K is, right? Because it's the expression of the ratio of ADP to ATP at equilibrium, right? And that's what the equilibrium constant represents, right? So that's what they're asking for. So it's an unknown, X. They gave us delta G, which is -30. They gave us what RT was. They didn't give us a temperature, but they gave us what RT was, which actually made it easier because we don't have to do any math ourselves, which is 2.5. And we're given an ln x, and we're solving for x, right? First step, divide both sides by 2.5. 30 divided by 2.5, simple math, you should be able to do just on your own. It's 12, like using just long division. It's 12. So ln x equals 12. And I guess this is where you guys had encountered the issue, where how do you solve natural log? Well, this is the same, and this I mentioned before when I was covering, I believe, acids and bases, when I were talking about pKa's. So what this essentially means, what this question means is e to the 12th is equal to x. So e to the 12th is equal to x. And so let's see how that works. So you know that ln x is just log, is just a natural log base e. So you know, if you want to do reverse, just like if you were multiplying here, so you multiply 2.5 by ln x, in order to kind of like get rid of the 2.5 on this side, you have to do the opposite operation. You have to divide both sides by 2.5 in order to get rid of this. You have to do the opposite operation. If you're doing natural log, the opposite operation is e. So if you had e to the ln x, it would cancel out and you'd just be left with x on this side. And then you'd also have to do the same to the other side, which is just e to the 12th. So e to the 12th equals x. And x is what you're trying to find. So x is equal to e to the 12th, which is D as the right answer. Okay, and same thing works if you were given, instead of ln x, if you were given log x. Log is just to the base 10 instead of base e. So 10 to the log x, and you say that this equals like 5. This cancels out, you're just left with x equals 10 to the 5th, right? In order to cancel out an ln or a log, just do the opposite operation, just like you would if you were multiplying, you would just do division. If you're doing ln x, just do the opposite operation, which is e, or in the case of a regular log, 10 to the power. And then you can cancel out this. You're just left with e, and then e to the 12th. Does that make sense? Does anybody want any more clarification? Like I mentioned, I know this was like a more involved question.
Can you explain how you did the log again?
Yes, okay. And Opal asked, will the MCAT do this test? Yes, it will. Yeah, and you need help starting up the equation, that's fine. Just you had the equation like here, you know this is you came in with this. You just had to figure out what you know and what you don't know. You know what delta G is, you know what RT is. K is what you're trying to find because that's what the question is asked for. It gives the expression of ADP to ATP. ADP is the product, ATP is this is the reactant, right? And it told you that the concentration of P, which is the other reactant, is 1, and H2O is always 1, so it's always removed. But yeah, I'll go over the log again. I'll go over the log again in a second. Let me just clear this. Okay. So we have, say, ln x is equal to 12. This is what you have to solve, right? If I was to give you 5x equals 10, how would you solve this to isolate x? Well, you would do the opposite operation. So it's 5 times x. So you would do the opposite operation, which is division, right? You divide both sides by 5 in order to isolate x. 5 cancels out with 5. And then this cancels out with this, x equals 2, right? That's simple, you all know that. What's the opposite operation of ln? Ln is just log to the base of e, which is the natural log. In order to cancel this out, you would just e to the power of both sides. Just like with multiplication and division, e and ln cancel each other out. So it's x is alone, isolated, and you're just left with e to the 12th on this side. Yeah. So you just make sure do the opposite operation. Ln, the opposite operation of an ln is e to the power of. E to the power of ln x, it cancels the ln, x is the only thing left, right? Just like here, 5 times x, divide both sides by 5, you just have x alone. Here, e to the ln, x you cancels out, x alone. Whereas this side you keep, so you just took whatever number this was and you divided by 5, you took whatever number this was and you did e to the power of it, right? And e to the power of 12, and that's the answer. Any confusion, any questions?
Sorry, let me mute myself.
Can you hear me?
Yes, I can hear you.
Oh, so I was asking, you had, at the end of the problem, you showed us, you said if it said log, you showed us how to do something, but my head fell out. I was asking if you could explain that.
I'm sorry, I had trouble hearing you. Could you speak a little bit louder, maybe?
Hello? Can you hear me now?
Yes, I can hear you, but the question is a little bit kind of like hazy. Could you just speak louder and like a little bit clearer, just so I can hear?
After you explained this the first time, you showed us, you was like, if it said log, let me show you how to do that. That's why I was asking you to really
Right.
explain.
Okay. So you know what ln x is? It's just log, and you know how logs have a base e of x, right? Whereas sometimes you'll also be asked log, and this log base e is just called ln. Like they like it's used so much they have a shortcut for it essentially. Whereas like you may also be asked this log of x, and this again is used so much they have a shortcut for it. What the full length version of this means is log base 10, right? And if you wanted to do the opposite operation of this, just like here, you e to this power. If you want to do the opposite operation of this, it's 10 to the power of log x. Again, 10 and log base 10. This is essentially what this means is log base 10. They don't give you a number under the log, it means 10, and that's the only one they'll ever give you on the MCAT. It cancels out and you just have x on the bottom, and you just are left with x, just like you were here. Ln and x cancel out, 10 and log 10 cancel out. Does that make sense?
Yes, thank you.
Mark, did you say the opposite operation of ln is e to the x? Mark?
I'm sorry, could you repeat that?
Did you say the opposite operation of ln is e to the x? That's all I want to know.
The opposite operation of ln is e to the power of. So it's not e to the power of x, it's e to the power of ln x, which cancels out and essentially, yeah, so it's e to the power of, just like you wouldn't say the opposite operation of multiplication is x divided by 5. It's just division, it's divided by. Just like here, it's ln, the opposite operation of ln is e to the power of.
ln x.
Yes, the opposite of ln x. So if you wanted to cancel out ln x, you would do e to the ln x.
Okay, okay.
Like, just like this, right? Okay.
I think I got it now. Perfect.
Yep. Okay, any other questions about logs, ln's, or anything that I covered here? Maybe k or anything here? Anything at all? Nope.
How was I supposed to know that K was the ratio of the ADP over ATP?
Right. This was I don't know if you maybe were not here for that, but it was a lecture that I gave on kinematics where I covered equilibrium constant. KEQ, which is what K is.
Products over reactants. Okay.
Yes, it's concentration prod over reactant.
Okay. Yeah, I was here.
Yeah. And so the reason is there's 2 products. So they gave you 2 products and 2 reactants. ADP is product 1, PI is product 2, H2O is reactant 1, ATP is reactant 2. H2O you always get rid of. Water you just get rid of in any KEQ equation, just in general, because it doesn't matter. So you're only left with 1 reactant, 2 products. They told you the concentration of PI was 1. So that means you would put it here as PI, right? But it's 1, so essentially it just doesn't, it cancels out as well. All you're left with is just concentration of ADP over ATP, and that's what KQ is. And that's exactly asked. Which expression gives the ratio of ADP to ATP?
What happened to the reactant? It just disappeared also? I know the product was 1, it disappeared. So what happened?
Water you never include in this equation, just in general, whether it's on the product side, reactant side, anywhere. Water, if you have in an equation, you always just don't use it because it's complicated as to why, but it's like very complicated as to why, and you need actual like thermodynamics for it. But
no, but we're not concerned about water. We're concerned about the ATP. So okay, we got rid of the numerator product. What happened to the ATP? What's the number?
It's in the denominator right here. So this is ADP. This thing is ADP. This thing is ATP. So it's product over reactant, ratio of product to reactant.
That's 2 unknowns, Mark. I'm sorry. That's 2.
Yeah. Yes, but these 2 unknowns are these 2 unknowns. A ratio is not 2 unknowns. A ratio is essentially 1 number. Okay. The ratio of y to x can be written as z, and you're just trying to find out what z is. You don't care about what y is. You don't care about what x is. You care about what z is.
I see now that you got it. Now you did it. Okay. Now that you did it this way, that y over x equals like the rate. Okay.
Yeah.
All right, I got it now.
Yeah. So if it doesn't ask you what ask you what the ratio is, and the ratio is KQ or K in this.
Yes, perfect. Okay, it's not 2 unknowns. Got it.
Yeah. Any other questions? If not, I can move on. Okay. All right, so this is another common topic that they may ask on the MCAT, and it essentially revolves around one equation. So it's a formula you may be asked is Q equals MC delta T, commonly called Q equals MCAT, just because it looks like that, like the delta looks like an A. Q equals heat, M equals mass, C equals heat capacity, which we'll cover, and T equals temperature. In this case, it doesn't matter Kelvin or Celsius because we're doing a delta T, so Celsius, Kelvin is the same thing. Doesn't matter. Heat is different from like temperature. Heat is also like an energy, right? And I'm not gonna go over how it relates to enthalpy or internal energy because it's not really tested on the MCAT. It's not important for the MCAT. But just know that heat and enthalpy are related but different. And it's very different from temperature. It's completely different from temperature, right? Heat is completely different from temperature. C is heat capacity, and it's a measurement specific to each individual substance. So water has its own heat capacity, like iron, steel, everything has its own heat capacity. Every different like material has its own heat capacity. And what it essentially means is how much heat, how much energy is required to increase the temperature of 1 gram of the substance by 1 degree, either Celsius or Kelvin, it doesn't matter. And you can see that in its units. Its units are joules per gram Kelvin, right? Yeah, and Janelle posted the Kelvin to Celsius relationship in the chat. And as you can see, if you're doing a change in, it's the same thing because it's addition, right? Okay. But I just want to say, like, they'll always, if they give you a specific heat capacity, they'll always give you a unit for heat capacity if you don't remember exactly what it is. And here is how you can think about it. How many, so this means how many joules per gram of the substance is needed to increase the temperature by 1 Kelvin, to change the temperature by 1 Kelvin, per Kelvin, right? Per gram per Kelvin, right? And so, for example, something like, you know, that metals like iron, like it's very easy to heat up iron. It's a very good conductor of heat. So they would have a very, very small heat capacity, maybe like 1. You only need 1 joule of energy to actually per gram of iron to raise the iron's temperature by 1. It's very easy to heat it up. Whereas something like water or air, which are inductors of heat, they don't really, their temperature doesn't really change very well with heat. They would have high heat capacities because you would need to put in a lot of energy, a lot of joules into them in order to change their temperature by even 1 degree, right? Does that make sense? Metals, good conductors, have very low heat capacity. Inductors, water, and even more so like air or something like that, have very high heat capacities. Does that make sense?
Yes. Would they MCAT ever give us other units for the heat capacity? Like I think I've seen problems with joules per gram per calorie. Would it always be the gram per Kelvin?
From what I've seen, it's only in joules per gram per Kelvin. If it's specific heat capacity, it may be a different quantity that they're asking from, yeah, something else, right? Okay. Maybe a different quantity that they're asking for something in the passage or something. But in this sense, heat capacity is only in joules per gram Kelvin. Okay. Again, it might be Celsius, for example. They may give you joules per gram per Celsius. It doesn't matter, kilojoules per gram per kilojoules per kilogram or whatever, but essentially it's the same thing. And Q is heat, which is measured in joules, right? Or joules, kilojoules, doesn't matter, right?
Yeah.
Heat is a unit of energy.
Yeah, and another thing, I try to think when I think something becomes a little difficult, I try to relate it. So heat capacity, the reason why I will fill my pool with water and not oil is because it takes a lot of heat to raise the temperature of my pool water. Versus if I fill my pool with oil, it's not going to take a lot of heat to start.
Exactly. And,
Okay.
and
Mhm.
that's exactly right. And same can be applied to metals, water. Like it's very easy to heat up a metal, much harder than it is to, much easier than it is to heat up water. It's much easier to heat up water than it is air, for example, or something like that. Yep. But yeah, exactly right. Think of it as like that. Well, that's a good way. But yes, there are other problems with filling up the swimming pool with oil. So I want to talk about this, which is this diagram, and this is an important diagram that you may see sometimes, or that you may use. So for example, let's say you start off with solid. We'll use water, for example. You start off with solid, ice. You, on the x-axis is energy input, which is Q, heat. On the y-axis is the temperature, right? See how ice starts off here at point A. As we put in more energy, it linearly increases, the temperature linearly increases as we put in more heat. So say like we had like a blowtorch, like a fire, a stove or whatever. We had some kind of like heat source. As we add more heat, the temperature increases linearly in accordance with the formula Q equals MCAT. Then it reached a point. This point B is when it's reached its melting temperature. So the melting of temperature of ice is 0 degrees Celsius. So at this point, it's 0 degrees Celsius. At this point, you put in your blowtorch back towards the ice. And as you notice, you put in more heat, but the temperature doesn't change. It always stays at 0 degrees. This red line, it represents the phase change. The ice is slowly starting to melt into water. As you put in more fire, the ice changes more to water, but the temperature doesn't increase. It's still 0 degrees. This is important, right? Until this point C, the temperature will not change at all, right? And at this point C, this represents when all of the ice has melted fully into water. There's no more ice left. Once there's no more ice left and it's all water, you put in more heat, more fire, then the temperature starts to increase linearly again, as you can see. Then you get to this point D, and now the water has reached its boiling point, 100 degrees Celsius, right? And now, again, you added more heat, more fire, it doesn't change. It stays the same temperature, but at 100 degrees, but slowly as you put in more heat, more fire, it will turn from water to water vapor to gas, right? And then until it reaches this point E, in which all of the water has fully evaporated, there's no more water left, liquid water left, it's all gas, then you added more heat, it'll raise. This is an important concept, and so like when you're at your melting temperature or at your boiling temperature, in either way, if you add in heat, it won't change the temperature, it'll only change the state of matter, right? It has to fully be like in between in order to change temperature. Does that make sense? Like, anybody have any questions about that? So once you're at your melting point or at your boiling point, you added more heat, the temperature doesn't change, but the state of matter changes.
Mark, I'm so sorry, sir. I have to be asking all these questions. As far as this graph is concerned, the question I've seen on the practice exam is which one of these phases is endothermic versus exothermic? Like, is the vaporization or fusion? So that's what messes me up, because they never ask it this simple, because you could just look at the map and figure, but they'll say which is endo, which is exothermic. Are you going to go into that? Because that's
so first, what I was saying with this graph is they're not going to show you this graph and ask you a question. You will have to have this graph in your mind. They'll give you the question in words and the answer is this graph, right? So they may ask you if you had, and actually an off-hour, somebody came in with this question. I don't remember who it was. Somebody came in with a very question like this. It was like, if you had ice, say at a melting temperature at 0 degrees Celsius, and you turned on like a Bunsen burner or like a stove for like half a second and then immediately shut it off, what would happen to the ice? And the answer was, it wouldn't change. The temperature would be exactly the same, and some of the ice would have turned into water, right? And you can see, so if you had ice at 0 degrees Celsius, so the ice would be right here at point B. You turn on a Bunsen burner for like a second, and then turn it off. You're now going past this, and then you're here now at this point. And that's what happens. So you notice the temperature doesn't change, and the ice is not fully melted, because if it was, it would be here at point C. but it's partially melted, right? And that's exactly what happened. The temperature wouldn't change, but the ice would be partially melted into liquid, or particles. Yeah. Does that make sense? So they may ask you a question like that, where they ask you in words, does the temperature change or does the temperature not change? And you have to know, and in your mind, you have to visualize this graph and then see which point at the graph am I at the start and at the end. Does that make sense, Opal?
Okay.
I'll say this: vaporization and melting are both always endothermic. If you're going from liquid to gas or solid, if you're going from liquid to gas or from solid to liquid, it's pretty much always endothermic, right? You have to absorb energy, and you can see that from the energy output, right? It won't like naturally happen. You have to absorb energy in, right? Right. And like if you have like trouble memorizing this or like understanding this, think of, say, if you're cooking, if you're like using water as like boiling something in water. If you put it on your stove and you have like water with like a potato or something inside, and the water's boiling, as long as you leave like the water in there, or as long as you leave at least some water in there, it will never, like the potato will never go above 100 degrees Celsius, because it's stuck in this between D and E state, right? The water is not fully boiled, and that's why your potato will never like burn. If you have water there, or any food, if you have it boiling in water, it'll never burn because it's stuck at this 100 degrees Celsius and it'll never go above, right? Because it's stuck in here while the water is evaporating. All the heat is going into evaporating the water. It's not going into actually raising the temperature of the water once it reaches boiling. However, as soon as all of the water is gone in your pot, and it all turns to gas, immediately your food will start to burn because you're out of liquid. There's no more buffer, and all the heat goes straight into increasing the temperature, which burns. And that's why. Sorry, but isn't going from a liquid to gas releasing heat. So it depends on the substance, not in the exact equation, I think. Because so you need heat in order to increase the temperature, and you also need some heat to like kind of start the process. But yeah, once it goes through, it does release a little bit of heat. Yeah, so it's exothermic at a point, but yes. It depends on what the question is asking. Like you would have to give a specific question or to give a specific answer, right? It's hard to like tell based on like they wouldn't give you this graph and ask you something like this. For example, like Opal was saying, they wouldn't give you a graph like this and ask you something about it. This would like the reason I gave you this graph is more as it's an answer or a way of answering rather than a question itself, if that makes sense. Yeah. So yeah, so it depends. Usually, actually, in terms of enthalpy, yeah, it's actually so like I was saying, it's this is actually one of those cases where, yeah, I was gonna say this is one of those cases where actually things disagree. Entropically, yeah, so entropically, liquid to gas is favorable because going from liquid to gas is favorable. And through enthalpy, it's actually not favorable. You have to absorb energy in order to go from liquid to gas. That's why it can be exergonic or endergonic, but it's always endothermic is what I'm trying to say. Yeah. So that's why actually things at high temperature, like you need a high temperature a lot of the time to go from a solid to a liquid or a liquid to a gas, because you need to put in heat. So like I mentioned before, at high temperature, the entropy wins. At low temperature, the entropy loses and the enthalpy wins. If it's high enough temperature, the entropy will win, and being a gas is more favorable than being a liquid, if that makes sense. So it's one of those cases where delta G is depending on temperature, because entropy, it's favorable. Entropy for heat of vapor, like vaporization of liquid, of water to water vapor, entropy is positive. enthalpy is also positive. They're both positive. Does that make sense? So yeah, that's something you would have to like look at a graph for and look at the graph for and based on the temperature. Okay, so last slide before we end off for today. So I wanted to mention that thermodynamics only tells you if a reaction will or will not occur. If delta G is -10 or if delta G is -10,000, it doesn't tell you how fast the reaction happens. The delta G where it's -10 joules might happen faster than the reaction that's -10,000 joules. That's because it just tells you it's favorable or not favorable. It doesn't tell you how fast it'll happen, right? How fast it'll happen is only based on kinematics, which we did a separate lecture on, right? Kinematics of reactions, right? Like that's the speed of reactions, equilibrium constant, all of that stuff. So just because something has a very, very small delta G doesn't mean it's a fast reaction. It just means it's a very favorable reaction. It will happen for sure. And then lastly, and I covered touched upon this before, there's a difference between delta G and delta G standard. Delta G standard is the delta G of the reaction at standard temperature and pressure, which is STP. Standard temperature is 298 Kelvin or 25 degrees Celsius, and standard pressure is what atmosphere, right? Most reactions in biology don't happen at STP. They don't use this delta G standard, but in chemistry they do, because in chemistry you do it in a lab. In biology it happens in our body, and our body is not 298 degrees Kelvin. It's much higher. It's like I believe it's 313, right? Because it's not, body temperature is not 25 degrees Celsius. That's room temperature. Body temperature is about 38 degrees Celsius, right? So be careful because delta G actually is dependent on temperature. So delta G is dependent on temperature, as you can see from the equation. Delta H delta H minus T delta S is dependent on temperature. Delta G standard is not dependent on temperature. Delta G standard is at a certain temperature, right? So delta G standard of a reaction at 298, 398, 598 is the same because it's standard, whereas delta G of those three reactions is different. And the same applies to delta S and delta H. There's delta S standard and delta H standard, which also at STP. For delta S and delta H, you don't really have to worry about converting between standard and non-standard. It's very that's very nuanced, and it's like they're not covering that on the MCAT. Delta G standard to delta G you might have to worry about, and it's this equation: delta G equals delta G standard plus RT ln K, right? And this equation may look familiar to you. It's actually, we actually covered a very similar equation. This one, delta G standard equals negative RT ln K. This is actually how this equation is derived. It's actually how this equation is derived, because you know that at equilibrium, delta G equals 0. So if you had the equation I just showed, it's 0 equals delta G standard plus RT ln K. All you do is you subtract both sides by RT ln K. You move this to the other side, and you have delta G, and you have essentially this equation: delta G standard equals negative RT ln K, right? And at equilibrium, delta G is always 0. This is another thing I maybe didn't mention. Delta G is always 0 at equilibrium, right? And the way you get from delta G standard to delta G is through that equation. Okay. Any questions about anything on this page, or anything in general so far about this lecture? Because this is the last slide.
Yeah, Mark, I had an unmuted one. I just thought about the lecture in general. So I did believe in the Big Bang. So we went from a
Hey, Opal, real quick, just
exploded.
try muting, try turning
I
the
tried
volume
muting
off.
either. Oh my God.
Try turning the volume off on one of your devices.
Oh, okay. Let me do that. That's better. Okay, so if you believed in the Big Bang, so would the second law of thermodynamics say, I think the Big Bang says what? We went from a star and then we exploded and got all the planets. So that is why the universe is always going to disorder?
That's something you'd have to ask like an astrophysicist. So that's like not a question I would know. It's like way beyond the scope of the MCAT. And that's a question for like an astrophysicist. Yeah, I that's not a question for me.
I was
I'm
just
sorry.
trying to wonder
Yeah.
about you had a slide earlier saying could you put that slide back up about the universe going to disorder? And could you expound on that, please? That's all.
Yeah, like I mentioned, it's just like the law of thermodynamics that the universe can never, it's not necessarily it goes towards disorder. It's just disorder tends to be more favorable, and on like small scale, if you think about it, like on a small scale, disorder is more favorable than order. Just like we go from liquids to gas is not like it's more favorable to go from a liquid to a gas. And it just the universe, the entropy of the universe, the order of the universe can never, the universe can never get more ordered or more, the entropy can never increase, right? Or never decrease, I mean, I'm sorry. The entropy of the universe can never decrease. It always increases. Or it stays the same based on chemical reactions, yeah.
Okay, that makes sense. And then you gave that little caveat where you said there's a situation where even let me just read it real quickly. Sometimes something increased, but it doesn't necessarily mean the other thing increased.
Okay, right.
Okay.
So
Go over that again, please.
Okay, so if for example you're turning from a liquid to a gas, right? So like I mentioned how if you're going from a gas to a liquid, the entropy decreases, right? If the entropy decreases, that means the entropy as a result of that gas to liquid transition, something outside of that chemical reaction, outside of that gas to liquid transition, something else has to, the entropy of something else has to increase, right? So as a result of the gas of like water vapor condensing into water, something else other than the water vapor has to become like more disordered, right? Either through an increase in temperature, which is usually how it happens. So that's one way, like you increase temperature of like the surroundings, and the surrounding increases in entropy, right? As a result, and that's usually how it happens. But the entropy has to like change, right? Whereas if you're going from a liquid to a gas, that's not necessarily the case. Something outside of the liquid to gas doesn't have to change in order for the liquid to change to gas, if that makes sense.
And how would what would the MCAT do to test if we know that difference? What kind of question?
It probably won't. That was more for,
okay.
That was like more like a small point that kind of like I explained multiple times, but they probably won't realistically.
It
like
won't. Okay.
Yeah, that's like something a physics exam might ask you, like a high level physics exam, but that's not for us.